Hello, my name is Liam Dugan, and I'm going to be presenting Real or Fake Text, investigating human ability to detect boundaries between human-written and machine-generated text. This is work I've done jointly with my co-authors, Daphne Ippolito, Arun Kirubarajan, Sherry Shih, and Chris Callison-Birch here at the University of Pennsylvania. Okay, so we're talking about detecting machine-generated text. How does it actually work? So natural language generation is a process by which we use a neural network to predict a probability distribution over the next word in a sequence of words. So, for example, we have yesterday for dinner I ate. We feed that into a language model, and it'll give us a distribution over what the next most likely word is. If we do this over and over and feed back our predictions into our input sequence, we can generate fluent sounding text. This is much more common nowadays for people to know about, given the recent release of ChatGPT by OpenAI. This is a program that has made headlines for its ability to generate incredibly fluent sounding text. For example, here's me asking it to generate a high school essay about the Great Gatsby. And not only does ChatGPT know about the Great Gatsby, but it also knows the style of a high school essay, the 5 paragraphs, and it writes it quite well. So there have been a lot of news articles about how ChatGPT marks the end of creative writing and that AI writing detection is a losing battle. But is this actually true? Should teachers really be on alert for inevitable cheating? And are teachers not able to detect this text? There are reports of people being able to detect it. For example, this one that says it's a clean style, but it's recognizable. I would say it writes like a very smart 12th grader. And there's a particular odd wording used that was not wrong, but just peculiar. Like if you were teaching someone how to write an essay, this is how you tell them to write it. So is this just confirmation bias? Is this person out of their mind? Can people detect generated text? So this is what we're going to be talking about today. And the traditional way that people do this is by doing something called binary detection task. So what binary detection is that you're given a passage and you're asked whether or not it's written by a human, and you have 2 options, yes and no. So this actually has quite a few problems with it, though. Um, the problems start, we don't actually learn why the user selected either option, yes or no. And so we don't have any insight as to how they're actually doing the task. The setting is also unrealistic because typically in practice, you don't have something completely generated by a machine, but instead you start to prompt it. You give it a few sentences and then you let it continue on from the sentences. Also, when you're an annotator and you're being given a bunch of 5-paragraph essays, you might not be reading them as closely and you might get bored over time. Similarly, if your incentives are to do as many annotations as possible, it might not be a great way of seeing how a very careful reader might fare on the task. And then finally, there's no interactive feedback. Annotators don't get told whether or not their guesses were correct until the end of the task, which means that if they had misconceptions about what generations actually look like, those misconceptions are not corrected, and therefore this affects their actual accuracy. So our research goal was to fix these problems and also to gamify the detection task to conduct a large-scale study of human detection. In order to do this, we made the Real or Fake Text game. This is a website that we wrote, and it is public at ROFT.io. And the website primarily focuses on the boundary detection task, i.e., selecting the sentence at which a passage transitions from being human-written to machine-generated. Here you can see that in the blue we have our human-written prompt, and then we have a machine-generated continuation. And the goal of the player is to decide whether or not this generation was written by a human. So if they select it's all human, they're given another sentence in the generation. And then so on and so forth until they think that the sentence is machine-generated, at which point they select machine-generated and they're asked to give a reasoning as to why they thought something was machine-generated. Once they hit reveal, they're actually told the correct answer. In this case, the annotator was exactly perfect and got the exact boundary sentence. And then they're also given points, which are added to their profile, and they're on a leaderboard, which incentivizes people to want to get as many points as possible. Because it's important for the talk, it's worth noting that players earn exactly 5 points for guessing on the boundary and 4 for guessing one sentence after, so on and so forth. And we're going to talk about a player's detection skill as a function of their mean score, which is the average score they get per each generation. So what are some advantages of ROFT? So ROFT is a more realistic setting, whereas a passage is not completely generated, but partially human and partially generated. Also, the extra sentence-level interactivity forces people to actually read carefully and keeps them engaged. We also collect data on why decisions are made. Not only do we know the exact sentence that the human annotator thought was suspicious, but we also know why they picked that sentence in the form of our error annotations. And this can be used as an educational tool for the public as well. So it's also a good way to teach people how to detect text. Okay, so what do we have on the platform? So we included generations from many different genres. We have stories, we have news, and we have recipes. And in order to generate the continuations for these genres, we primarily used a GPT-2 XL with nucleus sampling of p equals 0.4. Another advantage of the ROFT platform is that we could systematically vary a lot of elements of the model behind the scenes and do comparisons that way. And we'll talk more about these findings later. Uh, so our study population was 241 students. All of them were senior undergraduates and grad students from our artificial intelligence course. We want to note that this population is not at all reflective of the global population. So you should not interpret our results as how good people are at detecting generated text broadly, but rather as this small sampling. And we encourage more people to get a more representative sample of actual people in the world. Okay, so from September to October, we collected over 20,000 annotations from our participants. And it turns out that this is actually the largest human study ever performed, which we're pretty pleased about. And also, our data we've released now publicly at the following GitHub link. So please feel free to check out our data on your own and possibly do some analysis on it if you so desire. Okay, so what did we end up finding from our study? So first things first, the elephant in the room question, can humans detect generated text? So it turns out that our players are slightly better than random chance, but the picture's not looking so good, right? 23% accuracy is 1 in 4. And likewise, correct side of boundary accuracy paints a better picture, but not by that much, considering that chance is 50%. But let's take a closer look. Clearly, we can detect better than random chance on average, but what's really going on here? So if you plot a histogram of the mean score of all 240 participants, you find that the histogram actually has a pretty long tail, both for mean score and standard deviation of score across different rounds of the game. Even more interesting is that these two tails are actually the same players. Of the players that got mean score of 3.8 or higher, they also had standard deviation of 1.8 on average. Which means if you return to this original chart and you add in another column, for our best player, you get a totally different picture. 77% chance perfect guess accuracy is very high. Likewise, 90% for correct side of boundary. Another interesting thing is that we conducted inter-annotator agreement studies by giving 3 players the same generation. So every generation we had 3 players that annotated that, and we tested how much they agreed with each other. And across all players, there was slight positive agreement, but among the top 10% of players, there was quite substantial agreement, which is to say that good players are making similar errors here. And so what's going on? Can we train the bad players to perform like the good players? Okay, so in order to test this, we wrote a guide document called the Realer Fake Text Guide, and we gave it to a subset of our population. This guide talks about the different signs of machine-generated text, and this was written from our own personal experience attempting this task. We also go over features that may be misleading, such as bad writing, because humans also write badly. And also we give some concrete examples of generated text, and then some of these, we explain why this text is clearly generated. Like in this example, the model forgets what the score of the football game is and changes it halfway through the passage. And this is something that you would only be able to detect if you really read it closely. Okay, so we split our population up. Like I said, we gave the document to one part of the population, and we also gave that same part of the population, this is group B, we gave that part of the population extra credit proportional to points scored. And we hope that this incentivizes them to make more effort to actually get better at the task rather than just clicking through to do as many annotations as possible. Group A was our control group, and these students received fixed extra credit no matter how much they did, and no guide document at all. And so it turns out that if you plot their mean score over time, we notice that the students in Group B actually had pretty substantial improvement over time across 100 annotations. This is awesome, and this is a great finding, but we want to know more. We want to dig deeper. So what are our players actually learning when they get better over time? So let's return to our error taxonomy. So in our error taxonomy, there are different types of errors. Some of them are basic fluency, but some of them are more substantive and they're more nuanced. So there's grammatical errors, but there's also things like common sense errors. In fact, if we group the average score for annotations that said a specific error type, we see that there's a large difference in how often people got good scores when they said grammatical error versus common sense error. So to note, people who notice common sense errors have almost 1.5 times the score of people who notice the more simple errors, such as grammaticality. And these error types actually change across the genre of text as well. So we note that recipes have almost 3 times as many common sense errors as do stories in New York Times, despite the model being completely identical. Likewise, New York Times, if you look at the gray pie slice, has almost twice as many generic or uninteresting answers as short stories and recipes. This is also reflective in how easy each of these genres are to detect. We note that the news and stories are the hardest genres to detect, and the recipes are the easiest, partially because recipes are structured and require a lot of common sense reasoning that models have traditionally struggled with. Okay, cool. So this is the end of our human detection findings. But what about our model comparisons? So we found that humans improve over time. We found that there are different errors, but what happens to our detection accuracy as we change things about the models? So as a reminder, our main system is GPT-2 XL, but we want to vary the size of the model, the strategy of decoding, and fine-tuning. So our first thing, bigger models are in fact harder to detect. This matches exactly what we would expect, and GPT-2 XL is much, much harder to detect than GPT-2 Small. We note that as models get larger, and they have gotten significantly larger since GPT-2 XL, they're going to get increasingly human-like and hard to detect, which just underscores how important it is to really try your best to detect generated text, or at least train yourself. We also note that the more diverse the text is, the easier it is to detect. And this is also validating from previous research. Nucleus sampling is our decoding strategy, and the way nucleus sampling works is that we restrict the probability distribution to only a certain percentage of the probability mass when we're sampling the next token. And we note that when you sample only the most common token, it's very difficult for people to detect. But if you sample completely randomly from the distribution, it's the easiest to detect. Interestingly, for automatic detection algorithms, they have the easiest time detecting this argmax sampling. And so this goes into another research direction, which we'll talk about in future work, of having joint human and algorithmic detection strategies. Next, we note that fine-tuning actually doesn't seem to make detection all that much harder. So when we fine-tuned GPT-2 XL on recipes, we note that our perplexity was cut in half, yet the fine-tuned model was still easier to detect by our players than the vanilla model. While obviously more work needs to be done in this area, such as doing it in different domains, we want to underscore that low perplexity doesn't necessarily equal good quality, and that we should really focus on what makes text high quality rather than just going low perplexity all the time. Okay, so what are our takeaways? First, there's a wide variation in detection ability, and it's not fair to say that all humans can only detect no better than random chance, because certain humans that are very, very good at reading generated text might actually detect quite well. The next finding is that you yourself can train to spot generated text. We note that this is unclear whether or not this extends to models that are as big as ChatGPT because we didn't test on them. But nonetheless, people should definitely learn the basics. They should know not to look for grammatical errors and know the sorts of errors that models tend to make. Finally, we note that models make different errors on different genres of text. The same model on recipes will make common sense errors, while the same model on news will make generic errors. This means that the detection skill that you learn on recipes might not transfer across genre or even across different models, and that you should focus on training areas where generated text is the most harmful, and that you should continually be updating your skills as newer and newer models come out. For future work, we think it's really promising to look at how to develop tools to assist humans in detecting generated text. Likewise, we want to use the insights gathered from human studies to guide how we develop automatic detection systems. Instead of just slapping BERT on a data set of GPT-2 generations, we want to look more at these sorts of common sense errors, these document coherence errors. Likewise, we want to look more into what makes text high quality, not just whether or not text is human or generated. And we think that this will have a very large impact on how models perform going into the future. Okay, that's about it for our talk. Thanks so much to all of my amazing collaborators. Please check out the dataset if you have time, and thanks so much for listening.